Hello everyone. First of all, I would like to thank Luca and Guillaume for the invitation. Today I'm going to talk about a static analyzer called MemCAD, which was designed with a bunch of people, too many of them to cite in a single slide, so I will cite them when I come across specific topics. So what are we going to try to do here? Well, first we are doing static analysis, which in general is a way to compute semantic properties for programs using some kind of conservative approximation. So we are going to use abstract interpretation. And it has a very wide range of applications, some of which are not so commonly investigated. So I'm just going to go through a few of them. So for instance, many people and many tools work on basic safety. So things like proving absence of errors in programs. So for instance, I worked on one tool called Asray, but there are many more that also try to go for this, like Pharmacy, also Sparrow, which is developed at SNU, not far from here, and many more. So one thing a little bit further is memory safety, so which is to try to prove, again, absence of memory of errors, but for programs that are manipulating complex data structures. So among the tools that work on this, I will just cite one, which is Facebook Infer, or now Meta, should I say. And if we go a little bit further in the safety space, we still look at safety properties. So one interesting place to be is functional correctness, which is to prove not only that the program will not crash, but also that the outputs meet the spec of the function, which is much more difficult to prove than the other properties above, and which is what we are going to look at today. So, and of course, I mean, for the sake of completeness of the discussion, I will just cite a few more that people could also look at, like resource properties. We are not going to do that today, but we could adapt some of our analysis for this. Also, liveness properties like termination, so we are still far from that, but actually also combining the analysis we are going to talk with liveness brings something really nice, which is total correctness, namely trying to prove that a program does exactly what you expect it to do and never always terminates, never crashes. I mean, basically the strongest thing you can expect in the realm of trace properties. And we could also go into the security area, which we could also adapt some of the analyses we are going to talk about today to do. So essentially what we are going to focus on, like I said, is trying to go to the functional correctness from basically tools and abstractions that are more oriented towards the first thing. So this is quite difficult, so we are going to see a number of abstractions for that. So how did we basically do that? Essentially we developed a static analyzer I'm going to talk a lot about today, which is called MemCAD, for memory composite abstract domains. And the idea of this project was to construct and combine abstract domains for data structures from the bottom up. That is, we just design small abstract domains for specific structures, actually maybe not so small, but at least smaller than if we try to have a monolithic approach which supports everything, and to combine them to have something more expressive. And I am going to talk about some of these combination aspects, which is very important. So essentially today we are going to talk about a tool which is very much centered on memory abstraction. So we are going to first talk only about the memory part, which is not so recent, but which is absolutely required to go a little bit further and to also have abstractions that can talk about content of data structures. Okay? We are going to talk about how we can combine value abstraction together with this memory abstraction, and also to discuss a little bit how we turn all this into some abstract interpreters that is basically the design of which is directed by the semantics. Okay, so here is a very brief timeline. So I'm not going to talk about all these lines, but just give a few specific points. So essentially this all started in 2007 when I started to work with Boryue and Cheng on tools that was called XISA, which is essentially a prototype of some inductive-based shape analysis, which is basically the foundation of what we are going to talk about today. And after adding a few abstractions, it turned out that we pushed this approach quite far, and the full rewrite of the analysis was required. So this happened in 2011, and starting from that on, we added many abstractions, some of which we are going to talk about today. Like, for instance, I'm going to talk about how we added set abstractions and sequence abstraction to this analysis. And now we have a tool that starts to be quite competent, and we can apply it to try to verify things like functional correctness of a micro-kernel. So software is not very big, but the property we try to prove is extremely strong. OK. So what are we essentially trying to do? So here is a very simple example, a little bit contrived. Let's imagine you have some C programs that basically construct some list L and at some point calls a start function. So this is very classical thing for young freshmen to implement. Now the question is, what if we try to prove things about it? So the first thing we could try to prove is just that it runs safely. And I would say that for quite some time, we have had static analyses that can do that pretty well. That is, you can just give, I did not detail all the code of the function, but that can basically prove that the memory accesses are correct, that we don't corrupt the memory anywhere. This is not so hard. Now the question is, what about trying to prove that this program produces the expected output, which is sorted data structure? Okay, so this is much more ambitious goal, and typically people who try to do that use different approaches like interactive proving or some program verifiers that will actually require the user to provide some invariant. And we are not going to require this, so this is much more difficult goal. Okay, so essentially, in order to achieve this, like I said, we are going to have a requirement for some pretty expressive memory properties logics, but also to talk about content properties like sortedness, which is not something that you can typically find in memory abstractions. Okay? And also, one more that is implicit but very important is that we don't want to have a sort function that always returns a sorted list, but that is basically empty. We want it to return a list that contains the same elements as the input. So we have also to talk about relations across states. This is also quite technical, but very important. Okay, so in this talk, we are going to start with this memory abstraction description, which is not also new, but which is required to basically later extend it with content abstraction, which is going to be the second part of the talk. And in the last part, I'm going to talk about specific verification project, like libraries, micro-kernel, like for functional correctness. Okay, so let's start with memory abstraction. So essentially, when we look into programs that manipulate data structures, there are many abstract domains that we can use, and very often it is most convenient to be able to talk about separation. If we don't have a way to talk about separation, we are going to be in big trouble when we try to analyze, for instance, updates into memory cells, so which is the reason why people have introduced a little bit over 20 years ago something called as separation logic. So I will very quickly summarize it. We are going to use the principles of separation logic a lot in the next 20 minutes. So if I don't introduce it, it would not be very complete. I don't want to go through the whole separation logic. So I will just explain the main idea. So the main idea will basically fit into two lines, which is here. Essentially, we have some main connectors that are really capturing the spirit of the separation logic. So essentially, the most important one is the second one, but before we need to look at the first one. So what the first one says is just, we have a memory cell at some address A that contains value B. It seems very trivial. There is not much here. And of course, we are not going to go very far. The second part, which really brings, which is very helpful, brings a lot of power to separation logic, is to have this operator, which is called separating conjunction, writes down as star. And it combines essentially two heap predicates. So actually what is very important to understand is that each of these formula, H0, H1, or the whole H0 star H1 formula are all denoting set of memory states together with a footprint in a memory. So we are not just saying this memory state has some property, we are just saying this area of the memory state has this property. And when we combine H0 and H1 with star, essentially we just say that H0 and H1 are separate. Both of them enjoy, we have a heap that we can split into two parts. One part will satisfy H0, the other one satisfies H1, and we are talking about the whole lot. Okay, so this is very interesting when we try to do updates. So because in this way we can say one program will modify something that is in this region, and this one stays the same. So, and this will be absolutely critical for all the static analysis we are going to implement in the next 20 minutes or so. Now, is it enough? Well, usually not. So separation logic has many more connectors. I'm talking about a few of them here. And actually, I'm just not even citing them all here. There are some very important connectors I just skip. So if we just look at all these formulas and try to make a static analyzer, we have to basically make an abstract domain, the elements of which are those formulas. And essentially, if we try to do that, it's just not going to work. It's going to be very difficult to represent, very difficult to manipulate. Many operations are not going to be easy at all to compute, even in approximate form, very costly, not going to be very good. So essentially, what we are going to do today is to look at how we can construct some abstract domains that takes a fragment of separation logic. So we have to decide which formulas we keep. Out of all those we can express, and to design efficient representation for this fragment. So essentially, this is what abstract domain construction is about. You have a logic. Typically, you would like to represent everything, but you just have to think a little bit more, look at what you really need in program analysis, and do this fragment much more efficiently. OK, so one aspect of the abstract domain we want to design is that we want also to have an abstraction that is not ad hoc, that is not specific to just one data structure. There are a lot of static analyzers for memory out there, many of which are just dealing with, for instance, lists. We have also a lot of static analysis dealing just with arrays. And we would like to have something that does more than just one of these structures. So essentially, we are going to try to make the abstraction parametric. And this parametricity will later let us have one analysis. We give a little bit of information to it before we start it about what data structure we want to care for one program. And it will just run for that and not require for us to write another abstraction for another structure. Like, for instance, trees, because we only support lists. So how are we going to do that? Well, essentially, we are going to have some basic definitions that we require for users to provide, and that are just some extended version or enriched version of the type definitions. So I'm going to give an example. Let's assume that we take a very classical case. We take a program that will manipulate list of any length. We just use a conventional C list data type. I give 3 examples in the left with a typical representation that the null pointer means empty list. And we have 3 memory states with lists of length 0, 1, and 2. Now, how could we try to describe them all? Well, essentially, we can use separation logics to describe this, provided we add one thing that was not on the previous slide, which is induction. So we just write some inductive predicate, which is here. And what it says is that we have a predicate that corresponds to some memory area and says that A is the address of a list structure, if and only if we either have the empty heap region, which is essentially the neutral element for star, and A is a null pointer. So this describes for the blue area in the first state, where there is no blue area because it's empty. Or we have one list element with 2 fields D and N, and the second field N is actually pointing to the address of some other list. So we just write this predicate. And in fact, if we look at this predicate, for many data structures, we can actually generate them automatically from the type definition. We can just guess what the induction is and let for users to fix possible mistakes. Okay? So essentially, what we're going to do next is combine this small fragment of separation logic that we are going to choose with some inductive predicates, and we are going to build an abstract domain out of that. So how do we do that? Well, essentially, we are going to have abstract values that are going to boil down to finite conjunctions of graphs. So essentially, why do we take graphs? Because graphs are both very good representation. They can have a semantics that correspond to separation logics, as I am going to show right now. And also, they carry a lot of intuition regarding to what memory structures are. Like if we ask to programmers to describe what data structures they have implemented, very often they will draw some graph. And actually, it's quite likely that the graphs we are going to use inside the abstract state are not very far from our abstract graphs. So essentially, we have this notion of abstract states as a finite disjunction of graphs. Now, what about each of these graphs? We have nodes that are essentially symbolic variables that denote values. So this is quite important to understand. Each node in the graph will be will describe value. And actually, edges will carry basic predicates that are combined by separating conjunctions. So essentially, if we look at a graph, we have a bunch of edges. Each edge corresponds to some memory area, and essentially each node corresponds to some value in the memory, either address or content. And the whole set is basically a separating conjunction of things. Now, what basic predicates do we have? We have essentially basic blocks that are just described by points to edges like this. So essentially what this graph says is we have a block at address A0 with fields F and G, sorry for the small typo, with content A1 and A2, where these A0, A1, A2 denote values. And in the memory, this will look something like that. Okay? Then we have inductive predicates. So as I said, we are going to always start the analysis with the data of a bunch of inductive predicates, which can be either user-provided or guessed by the tool based on analysis of the inductive predicates. So we have actually two sorts of inductive predicates. If you give me the least inductive definition, you tell me you care for lists. Essentially, the tool will either introduce two kinds of predicates. One is complete structure that is basically going to be written like this and corresponds to a full list data structure. And the other one is actually very convenient when you have programs that traverse data structures, which is basically a segment of a data structure. So this is a segment predicate, which says that basically we have a list that starts at A0, but that's not quite complete. It ends with a pointer to some address, which is A1 here. And if you complete this with a list, then you get you get a complete list. So this is very important to have when you do structure traversal, for instance. OK, so when we design abstract domains, we need to care very much for concretization. So what the concretization will do here is it will take a graph into a set of states. I'm not going to expand it completely. Typically, this takes quite a bit of time. I'm just going to stress one very specific point of this concretization, is that when you concretize a graph, let's say you concretize this one, of course, we are going to map each edge to a memory region, which is just we read the separation logic semantics and we unfold it, essentially, so that's not very difficult. But we are also going to give a meaning to each node. And actually, this meaning will be essentially how do you place addresses in the memory. And this will be implemented with a valuation function, which is a function that that maps each of these AIs to some integers. So actually, this function is going to play a very important role when we are going to combine this memory abstraction with content abstraction a little bit later. OK, so in the bottom, I give an example. So here is an abstract state with one graph, with two nodes, with one list. So how can we concretize it? We have several ways. One is to consider the list is empty. You get that with this valuation that maps the content A1 to 0, and the other one that basically just unfold the list to a list of length 2. So that has a little bit more cells. But in both cases, together with the concrete memories that we get, we also get one of these functions new that is going to be used everywhere throughout the analysis. OK, so how do we do static analysis with that? Essentially, I just gave a very high-level overview of the memory predicates. Now, how do we do automatic reasoning? So first of all, what we do is forward abstract interpretation. That is, we are going to compute some function that takes a memory state, an abstract memory state before you run a program and produces one after. Okay? And the meaning of it is summarized by this formula, which is actually expressing something quite simple. If you start from this S, and if you have any memory plus valuation that is in the concretization of it, if you can run the program from this M and you get some M prime, then for some valuation new prime, M prime new prime is going to be in the concretization of the analysis result. So that's very basic statement, and that's how the analysis will work. And whenever we implement one abstract operation to handle condition test, assignment, memory allocation, memory mem-free, and so on. We are always going to think we have to maintain that. Okay? So how do we do? Well, first I will start with very simple case, which is assignment. So if you just have the command xf equal to y dereference g, then essentially what we are going to do in the abstract is very similar to what we would do if we were writing a compiler or a concrete interpreter. That is, we just evaluate the L value, except that evaluating the L value in the abstract means you want a memory cell, and a memory cell is going to be an edge. So we are just going to try to locate which edge corresponds to this L value. The R value corresponds to some values that we are going to store into the L value. So of course, we are also going to evaluate it into the abstract. And like I said, in the abstract, values are nodes. So essentially, we just want this R value to be evaluated into one node in the graph. So, and in this case, it's going to be very simple. If you take this abstract precondition, the L value is this edge in blue. I hope the color is clear. And the R value is going to be the node A prime, so A prime 2. So, and when you have done this evaluation, essentially you can just finish the operation by just performing the update. And in the abstract, the update is just replace one edge by another. OK, so not all cases are simple like this. If we just take also very similar statement like this one, so you just store into X the end field of L. And for some reason, you have some abstract precondition which looks like that. That is, L points to a Lie segment with some element in the end. Essentially, you want to read some field that goes out of node A3. Okay? Now, problem is you don't have any points to edge out of node A3. You have a segment edge. So at that time, the analysis needs to look into the inductive predicate that is given as a parameter to look into the least inductive predicate. And there are actually two cases. The most common case is that of a non-empty segment. So we just replace this predicate with one unfolded segment here. And then the rest of the update is completely standard, exactly the same as I have shown before. Or second case, the segment is actually empty. So all this area basically collapses down to the empty region. And in this case, we just map the new R value is this node A5. Okay? So the analysis essentially works like this. I just quickly summarize most transfer functions this way. OK, now very important operation when we do abstract interpretation is to actually generalize predicates. So we have several weakening operations that try to take one abstract state and turn it into something that is more general. So actually we have several operations like this. I'm just going to very quickly give the principle for one, which is abstract union. So if you are given two abstract states and you want to have one that over-approximates them both, how are we going to do that? Well, essentially, we are going to do it step by step. And the principle we are going to use is still based on separation logic. That is, we are going to take two abstract inputs. Each of them describes a set of memories. And we are going to infer some partitioning of the two graphs that is actually going to be connected. So I'm using colors here to denote the partitions. So the tool will come up with some blue partition here that describes a Lie segment between X and Y, and in green, a list tail that starts from Y. So actually, this inference of matching partitions is going to be interleaved with the other part of the join, which is to over-approximate each pair of matching partition with the same predicate. So it is much more complex than what I'm showing here, but the principle, you can really see those two steps. The second step is essentially we take the blue area, replace it with a common over-approximation, and do the same for the green. So we get this. Okay, and this defines join operation and also widening, so it has a termination property. Okay, so if we just quickly summarize this part with one example, so here is a C function that inserts an element into a list at a position that gets computed somehow. I give here precondition, which is one graph. What the analysis will do is do the abstract interpretation of each command one by one. And eventually, it will compute a loop invariant, which I give here, which says that we have a list L that points to a whole list here, which is actually split into two parts with a segment, which is actually pointed to by C, and a tail. And when we exit out of the loop, we are going to have an insertion that occurs right at this point. So we create a new element P. There is this memory allocation here. The value D is actually stored here. And we get a new data structure that actually describes the list with this new element inserted. Okay, so this is basically the first part of the presentation. We get this memory abstraction. And as you can see, what it shows in this program is that we start with a program with a state where L points to a list. We get to a state where L points to a list, but we have actually at this point no information whatsoever about the preservation of the content of the value inside the list. We have no information whatsoever about the position of D if we want it. So we need some more work in order to talk also about the content of the data structure, which is going to be the second part of the presentation. OK, before I get to this second part, I just wanted to mention that we have actually far more memory abstraction that I have shown here. I'm just showing here a small part of the abstract domain. We also have support for a lot of data structures. We have support for array abstraction. We have actually several of them that either partition arrays into contiguous segments, like the one in the top, or that partition arrays into non-contiguous segments, as seen in the bottom. We have also support for hierarchical memory abstraction. That is, we can say we have a data structure, some of which contains a data structure and unfold this way. So we have actually a lot of choice in the abstract domain, a lot more than what I can show here. By the way, how much time? What is? I forgot to ask. Sorry?
Still half an hour.
Half an hour, OK. And also, if anyone wants to ask a question anytime, please feel free to interrupt me. OK, so that is essentially what I wanted to say about the basic yeah, please.
Thank you. For the abstractions, are all of them available at all time, or do you select the abstractions you need based on the program at hand?
OK. So in fact, when you start the analysis, by default, you have a set of abstractions that will always be active. You can pass options to the analysis to enable or disable abstract domains. And essentially, it does not change during the analysis. What can change is how effective each abstraction is. That is, we may have the analysis itself can, to some extent, self-parameterize itself and say, at this point, we don't need this abstract domain and still have it here, but not represent any information in it. So I hope my answer is, but actually, it's a very good question, and maybe we can also come back to it in the second part, where there will be much more abstract domain choice.
Cool. Yeah, thank you very much.
Sure. OK, so actually, before I move to the second part, I wanted to make a few comments on implementation. That is, we often talk about how we design on paper static analysis. I find there is a lot of work to do to actually implement them well. So I will expose some of the choices that we use in this work. And maybe they are not, of course, the only choice you can make, but I can at least explain why we work this way. So for the abstract domain that I have shown so far, we use only immutable data structure. We use functional code. And so this is written in OCaml. And this is absolutely, this is for us, we found absolute requirement, which is, well, first of all, maybe ironically, it is very safe regarding to updates. That is, we have a lot of safety in the abstract domain in its implementation that just comes from the fact that we have data structures that are all immutable. We also get a lot of seamless sharing of common regions across different abstract states. So actually, we get a lot of power from this choice to have only immutable data structures. This reduces cost. This reduces also memory cost and also runtime. We can sometimes do very tricky things. For instance, when we have condition and we detect that two parts of the abstraction are physically the same, then we can immediately say the join is exactly the same. So we skip a lot of work. So essentially what we use as data structure is a lot of sum types in the OCaml setup with indexed maps and sets. So probably the data structures I use the most to implement those graph structures are here. Okay. And the analysis itself is almost purely functional code. We have references only for options and logging, basically. Okay, so now we are going to move to the second part, which is how do we do with collections. So far, we only talked about the memory layout. So if we try to also talk about the content, apparently things are going to be a little bit more difficult to describe. So we are going to discuss this a little bit now. So essentially what we wanted to do is to verify not only preservation of the data structures, but also something about the contents. We have to add to the abstract domain things that tell us this data structure contains a set of values or a sequence of values. Maybe if we want sets, we actually want sets with multiplicity, so multi-sets. So we want to augment the abstraction, which is so far just about memory, with the ability to talk about all these kinds of structures. So this is actually not trivial at all to move from one pure memory abstraction to something that can also talk about content. So essentially, we have to cope with a few abstraction problems. So one major problem is how to first find collection abstractions. There are fewer collection abstractions than you can find, for instance, for numerics or for memory. So maybe we need to design some. Actually, I will show a few of them. We also have to find how to engineer the combination. Like having two separate analyses is clearly not an option. We want a product abstraction where actually we can talk about the content together with the memory shape. And we want also the two abstractions to communicate, to exchange information seamlessly. So this is not a simple goal. So we are going to first start with a very basic first step, which is how to talk about value properties. So we are not going to do content right away. We are going to get to content in 2 or 3 minutes. We are first going to just imagine we would like to talk about lists, but we want to also add one more piece of information, which is that all the elements should be positive. That is, we are going to have operation in our program. It should not only maintain the fact that we have a well-formed singly linked list, it should also maintain the fact that values are all positive. So if we try to basically define this property and to write an instance like to parameterize our abstract domain, if we just write an inductive predicate, we can easily do it like this. So essentially what this predicate says is basically essentially the same as a singly linked list predicate. I just call it lpost because we are talking about lists of positive numbers here. And I'm just highlighting in purple some predicates that I attach to each of the 2 cases that were already in the singly linked list inductive predicate, and that have a meaning in terms of values. Okay? So actually there is one predicate that was actually 2 that were already here, but I did not emphasize this too much in the first part of the talk to basically separate concerns a little bit. But in the first case, we needed to say that we have a pointer that is null, because utilise corresponds to null pointer, so we already had a little bit of numerical information in there. Second is, in the second case, we have also a predicate that says that A should not be null, because we don't have empty list. And we also have this additional predicate, which is really asserting that the list is containing a positive number, which is the field A1 is a positive value. Okay? So we can write some inductive predicates that capture the meaning. So the question is how to extend the analysis so that it will do not only just basic singly linked list predicate without numeric information, but be able to care with such information. So essentially, we are going to get there in 2 steps. The first thing I would like to stress is that if we just try to write this predicate, and let's assume we can write predicate lpost in our abstraction, and we just hit the unfolding button. So we have this operation, which is unfolding, which I mentioned in the abstract precondition, so it is implemented in the analysis. What would it provide? What would it compute? And what insight can we take from the output of this unfolding to actually design the abstract domain? So let's look at what I would like my abstract value to look like. Well, if I unfold this lpost predicate, I will get an unfolded shape graph, like you can see here. well, which is not surprising at all. It is exactly what we saw in the first part of the talk when we talked about singly linked list. And I also would like to materialize those predicates and to say that some of the nodes that are symbolic variables representing values have some numerical information attached to them. So for instance, in this case, I want to say that A0 is non-null, and A2 is a positive value. So that gives a lot of intuition about what we want to do. If we want to have this combined abstraction, what we want to do is to combine together with a shape graph that I talked about in the first half of my presentation, together with some numerical abstraction, the dimensions of which are going to be not the variables in the program, but the symbolic variables, which are the node in the graph. So this is really the single most important bit that lets us move to the first part, to the second part of the presentation, which is each. So we are going to augment our shape abstraction with some numerical abstraction, but instead of saying things like variable x in my program contains a positive value, we are never going to say that. We are always going to say some symbolic variable, which occurs to be maybe the value of x or something else, has the property of being non-null or positive. Okay? So if we formalize this a little bit, we get a new abstraction, which is a combined abstraction. So we have already seen the first element of the pair, which is just one shape graph. And the second element is going to be any abstract element of your favorite numerical abstract domain. It could be intervals, it could be polyhedra, it could be octagons, it could be linear equalities, anything you like. You just take one abstract state of that domain, but you have to be careful for one thing, that the dimensions in n sharp should always be exactly the nodes in S. Sorry. If you just look at all the nodes in S, which I write as AS, these are the dimensions you are allowed to use in the numerical abstraction. Okay? And the analysis should maintain this at all times. So actually, this construction, you can view it as a kind of product of abstract domains. Actually, it's not quite a reduced product. It's something slightly different. Actually, there is a formalization of it done by Arnaud Venet some 25 or 30 years ago, which is called co-fibered abstract domain, which is a little bit technical, but this is essentially what it's doing. Okay? So now, if we talk about the analysis itself, what is going to happen is we are just going to have a choice that you actually do before you start the analysis. So this was a question a little bit earlier. How do we set up the abstract domain? Well, when we launch the analysis, we choose one abstract domain. Could be, for instance, any variant of the apron numerical abstract domain library. Could be something else. Actually, in our case, it is a combination of many of those things. We have a big reduced product inside the numerical domain. And the crux of everything is that the shape analysis, the shape abstract domain will maintain consistency of the symbolic variables that are in S and the dimension in N. That is, whenever we do an operation, maybe the dimensions in S will vary because we add edges, we add nodes and remove nodes. And we are going to modify N accordingly. Okay? So this is actually pretty tricky, but extremely powerful. Okay, so now I would like to get back to collection. I promised I would talk about content, not just values, so let's get there. So essentially what we have is, now we would like to express things like we have a list that stores a list of elements that we can express somewhere. So what idea are we going to use? We are just going to use very similar inductive predicates, but we are going to add some symbolic variables that denote sequences and that are going to also be used in the abstraction. So I'm first going to write a predicate. For now, I'm not going to care for the abstract domain. I will get back to the abstract domain in 2 minutes. So, and this inductive predicate will just tell us that we have a list that stores some sequence of elements that is captured in some symbolic variable E, the semantics of which is not a concrete value in terms of an integer, but a sequence of values, a sequence of integers. Okay, so here is the predicate. So we have, again, 2 cases. So A is the address of a list, the elements of which are sequence E, if and only if either we have the empty region, A is null, and the sequence is empty, or we have a non-null pointer, A is not null. We have a shape formula that basically describes what we are used to, with one small difference is that now the inductive call to list also carries some sequence symbolic variable, which I will call e prime. And we also have to have one more relation to capture the fact that the whole list contains sequence of element e. That writes down as e is equal to value a1 dot sequence e prime. We just concatenate them. So this is just an inductive predicate where e has semantics of a sequence, and we could actually have something that is maybe a slightly less expressive, slightly less strong, where we would just say E is a set, for instance, or E is a multiset. We would just write almost the same thing. We would not use the same connector here, but that's pretty much it. Okay? So essentially, this is how we add collection information into the inductive predicate. So now the question is, how do we concretize abstract states? How do we define and concretize abstract states? So the first thing is, so far we have used valuation functions that map symbolic variables that were variables a, a1, a0, a1, and so on into integers. We are going to extend this with one more case, which is symbolic variables of the form e, e0, and so on, and the meaning of which has to be a sequence of integer. Okay? So we are going to also use a combined domain, which is exactly the same as what I did for value. This is exactly the same definition. The only thing that changes is that now symbolic variables can be either just values or sequence sets or multisets. Once we have done that, well, all we need is collection abstract domains. So what we did is we did quite a few of them, actually. We have first a bunch of collection abstract domains that focus on sets, so they forget the order, so they abstract sequences, but only the first thing they do is the abstraction throws away the order of the elements and describes some set property. So we have inclusion and membership constraints. We have linear equalities, so with some algorithmic that is actually a little bit inspired from the car abstract domain, except that we operate on sets. And we have another abstraction that was designed by a PhD student I co-supervised with Evan Cheng, Arlen Cox, which is essentially representing predicates of that form. Intersection of a bunch of set variables is equal to the union of a bunch of set variables with a graph representation. A very, very tricky representation. So we can invent many more collection domains, include them into the analysis very easily. Okay. We also have introduced abstraction for sequences. So again, predicates are not surprising. We have emptiness, non-emptiness. We have linear equalities. We have size constraints, bound constraints, sortedness constraints. So actually, those mean that you also have connections together with the numerical abstraction. So actually, it's a very tricky reduced product of abstract domain to implement. Same for the min and max constraint. And the sorted predicate, we handle all the logics to talk about sortedness. OK, so I think now I probably don't have so much time, so I will skip this. 15, OK, well, no, I will not skip this. So this is just an example of one abstract state where we use our logics now to talk about not only the memory shape, but also the content, the collections that are stored inside the data structure. So we have here two variables, L and X, that contain some value. And actually, the content of L is the address of a list, the content of which is a sorted sequence of elements that are all greater than the value of X. So that's the kind of property we can express. I will not discuss in detail the concretization. The only thing I will stress is that now when I concretize this, I get not only a memory, some set of memory region, I did just draw one for the sake of space, but also memory region together with evaluation function, which map all the nodes and also sequence variables into values. And in this case, E is mapped to the sequence I, 8, 15, and 33. Okay? OK, so now if we talk about operations in the analysis, essentially we need to come up with sequence, set, multi-set abstract domains. I talked about the predicates. What about the operations? We have all the classical lattice operation, join, union, intersection, widening. top, bottom. The main operations are essentially add a constraint, so which is essentially what we call guard in most numerical abstractions. We just have to have a guard into the sequence abstraction. And we have also a SAT operation to check, to discharge collection constraint, which we have to use whenever we try to prove, for instance, that some predicate describes a sorted list. So we have to ask for the sequence domain, is this symbolic list E actually sorted? Okay. So, and when we implement this combined analysis, we have also to talk a little bit about how we combine those abstract domains in the code. So like I said, I like to make a few comments about the implementation itself. So for the data structures, I said earlier that we use immutable functional data structures. Now, how do we structure this? We use a lot of modules and functors in this OCaml language. So if you just look at any functional language with module system, this is what we use. So with essentially this convention that a module is very often one abstract domain, so module signatures for us are very important because they just list all the operations. And very often next to the operations, we have commands that describe the concretization, the soundness condition, right? So it's now, if we were to try to prove static analyzers, which some people have done in other projects, this would be a COC module with also the definitions of the soundness condition of each operation. So now that's for the base domains. Now, most abstract domains are parameterized by others, so we use a lot of functors, which are just ways to make modules parametric with other modules. And we use this a lot to say we just take some abstract domain and enrich it with some other functionality. We take numerical abstraction, we enrich it with sequence abstraction, for instance. So that's one functor. And actually, we found that this is actually a very useful programming setup to basically break down the design of the analysis in many small pieces, each of which can be designed separately. So it's actually quite, I mean, without this, we could not basically survive. So as of now, so in fact, while preparing the talk, I just said, how many functors do I have? How many abstract domains that are parameterized by another abstract domain? And I counted 50. So maybe I was wrong. I did that on the flight. So anyway. So some of these are actually just proper abstract domains that just add a bunch of predicates, some of which are actually not really adding new predicates to the abstraction. They are just factorizing some part of the operation implementation, some of which are doing logging, some of which are doing also some tracing that we use to improve the analysis. But essentially, this is the design that we follow. OK. So now I'm going to get back to the last part of the presentation, which is how to try to verify not just basic safety, but actually functional properties using that. So this is going to be a bit shorter, but we are going to start with an example. So let's assume we have some predicate, which is essentially the last one I introduced. So here we are talking about list together with the constraint of the sequence of the elements that are stored in it. So we can say A is the address of a list that contains the sequence of elements E. Then what can we do with that? We can actually specify logic triples that express that a function is correct. So for instance, here I just assume that I have two lists, L0 and A1, and I call some append function that destructively appends the list, the second one into the first one. We can write the precondition as a formula using our symbolic, inductive predicates. We can also write a postcondition, which is what we expect the function to compute. And once we have written this, we can just start the analysis. So what it will do is just translate, oops, I think nothing has changed in my side. I did not see the screen blink or anything. Okay, should I unplug and replug? But I believe, no, it's still working, so. Good, not so good. Okay, so back to this verification goal. Once we have written that, oops. Okay. So I hope it will work for more than 10 seconds. The analysis will basically translate the precondition into some abstract state, do forward analysis of the body of the program, and then just call some inclusion check function to try to prove that the abstract postcondition that was computed here is actually satisfied at this point. So imply this formula. So that's how we verify code. So the first thing we did after we implement this collection abstraction is just try to verify, so that was part of the thesis of Jocelyn Gier, who graduated last year, a bunch of functions for lists and trees, actually. So we took some libraries for lists, including some sorting algorithms, some merge sort, for instance, insertion sort, and we try to prove that they are safe. Well, that was not what we wanted, but also that they are functionally correct, which is what we wanted. So in fact, we just did the analysis first without sequence abstraction. We expected it to always succeed. We had a surprise that actually in some case, it does not succeed. That was a surprise to us because it shows that actually in this case, if we don't try to have a little bit more embedded into the abstract domain than just memory reasoning, it will fail. So that was quite surprising. But in most cases, we could prove safety without the sequence abstraction. If we add the sequence abstraction, the analysis costs quite a bit more. Actually, we reduced a little bit the slowdown since I made this table, but still cost is quite a bit more. And we have actually functional correctness proved into a large number of cases. So of course, this is just a bunch of the things we did, but I just wanted to show a few things, like some sorted algorithms. We could just basically prove that without any information inside the function, the analysis will make it to prove the postcondition. Same also for some operations on a binary search tree. So this is actually quite strong properties that were proved without intervention. We just specify the property, we let the analysis run, and it works. OK, so now that was not really our end goal. Our end goal was to verify some actual system software. So we just took some micro-kernel, which is called free at TOS. And we took one instance, so it's not a very big kernel. It's a kernel that is really meant to be used in embedded microsystems. So it's a few thousand lines of C code. You can parameterize it a lot. So we took one instance, and we just looked at the data structure we have in there, which are a lot more complex than what I have shown so far. So we have essentially some doubly linked list to describe the list of tasks that are ready, the list of tasks that are delayed, also with some order on some tick events to say when a task is going to be reactivated, when it is delayed. So it's actually quite a lot of things to describe. We wrote specification for that. So we have a file that basically says what is the invariant we expect for the operating system. That is, at one point, what do the data structures look like? And for each system call, we just also wrote one line, which is typically so we just expect before we run the system call to have this global invariant plus one condition, which is activation condition for the system call. And what is the post condition we expect for the system call is also typically the invariant of the OS plus one condition, like maybe we just turn one task from delayed to active. Okay? So we just wrote all these specifications, and we run the analysis for each system call, and this is what we got. So we have analysis times that range between less than a second to something like 2 minutes for each of the system calls of the instance we consider. So this is just a part. I mean, there are many more system calls and many more things, but total runtime is something like 300 seconds on desktop. And memory usage is just at most a few gigabytes. And for each case, we actually could verify the functional correctness properties that we specified. So actually, this is very strong properties that we got here. Okay, so what we would want to have in addition to that, which we don't do because we only do safety analysis, is termination. So actually, I think that would be a nice next project to add termination into this, because we would then get total correctness. But I would say that in this case, termination is really not going to be very hard because the loops have pretty trivial, well-foundedness arguments do not seem very difficult. So the big difficulty in each of these cases especially some of these system calls in the bottom, is to preserve the data structures that we have here and to reason over structures where we have typically 20 or 30 variables, each of which points to pretty complex data structures of this kind. Okay, so now to conclude, what are the key points that we wanted to get to today? So first, I would say that static analysis can be made very precise. So of course, it costs more, and we are not going to scale this to the Linux kernel tomorrow, that's for sure. But most people think static analysis is going to try to be quite cheap and not to compute very strong properties. Actually, here we prove, I think, that in certain cases, you can try to make static analysis able to prove very strong properties of programs. Maybe not the biggest programs at this point, but we can work on scalability from that point. Second point is abstract domain design. Takes a lot of effort, but is actually very rewarding. So in fact, when we started the Xisa project, we took a lot of time with Evan to craft the notion of valuation, how we map the nodes to values in the same time as we map these graph edges into separation logic predicates and memory regions. And this is essentially what let us later have this collection abstraction also fit into the framework. So a lot of work, but very rewarding later to work on the basics of the abstract domain design. And the last thing is also, the more we research in that area, the more we find there is a lot of unexplored space in terms of abstract domain design. That is, for the collection abstraction, I see very few people who try to basically design new abstractions, and actually there are a lot of predicates and representation of these predicates that could be tried to make this a little bit more lively, as was done for the numerical abstraction in the last 40 years. Okay, so these are just three main points. Now I'm very happy to take questions, and thanks again.
Anyone has questions?
Hello again. So first of all, thank you very much. It was really interesting. And can you say more about how function calls work? Because you have a separation logic domain, how do you do function calls in general? When you have to, because you have a specification for another function, you want to call that, or do you just inline the function?
Okay, good question. So in fact, let me get back to this here. So in fact, we do whole program analysis. That is, we assume here this is a whole program. So actually, this is not exactly how the analysis would work. Actually, we would just give precondition and postcondition for the main function, and then nothing else is annotated. So functions that are called by main, or even in this case, maybe append would call some other function. This is not annotated. Now, one thing we have that's not working for all abstract domains is support for recursion. Because, of course, when we have to handle recursive calls, this is like much more difficult. So actually, we don't have support for all recursive functions at this point and for all abstract domains. One thing I would like to mention is that actually I just have this timeline that shows some work that we could have explored more and try to port to all abstract domains, which was done in 2011, which was to do some relational stack abstraction. That is, when we have recursive calls, something that's very difficult is that when the call stack contains data structures that have to be abstracted together with a heap. And we essentially, we just said at that time, well, call stack is just data structures. We can just use basically the same data structure abstraction, which is very powerful. We found it works in pretty complex but small cases. Trying to make it work in all cases much better it would be a project that we still would like to work. So this is some idea we had in the past, more than 10 years ago, and did not completely maintain. So, but that's how we do for functions. Yeah.
Thank you.
Anyone else?
Yeah, Guillaume. Sorry.
Can you handle the side effects of data structures?
Sorry, I could.
Handle side effects of data structures.
Well, I mean, the whole analysis is handling destructive updates. So if you have, if you modify data structures that break pointers and replace pointers by others in chains, we handle that, yes.
Oh, okay. Thank you.
I mean, this is essentially one of the big points of the memory abstraction that we have. Otherwise, we could get to something less powerful, which is also very interesting, which is based on type systems.
Any more questions? No? Do you have support for user-defined data structures? If someone comes up with a new implementation of something.
Okay, so essentially, in fact, when we, so maybe I could have explained this a little bit better. When we start the analysis, so the analysis will give you a choice. Either it will scan the type defs and try to make one such predicate for each type def that it finds, and then you just get the analysis running like that. This works when you have fairly simple data structures, but if you start to have a lot of pointer relations that are really things that we cannot guess, they are really in your own designer's mind, then essentially you can just write such a predicate, and the analysis will take this as a kind of template to basically support the abstract domain implementation. So the short answer is yes, the whole point is to support user-defined data structures.
And you talked about scalability in the end. How far did you push this analysis? What's the biggest code base that you managed to analyze?
Okay, so I think biggest code must be the FreeRTOS instance, which is about 1,000 lines. For which we actually only do functional correctness. That is, if we just drop the precision, like I think maybe I can. That is, if we just do the same thing as we do here, that is, we deactivate some part of the abstract domain. We just remove the sequence abstract domain and say we just want to see safety. It will not work because the data structure invariant require us to come up with stronger arguments. So we have to go with this stronger argument to actually prove the code. It is about 1,000 lines of code and 5 minutes for this very strong property.
Okay, thanks again, Xavier.
Okay, thank you.